All right, welcome to Unit 2, Lesson 2. We're going to look at some alternate definitions of the derivative. They're all different but equivalent and very similar. And then we're also going to utilize a variety of different notational conventions for writing the derivative of a function. And these are just things that we need to know because some people like to write them in different ways. And so we want to be able to understand what someone, or in our case, what the College Board, who makes the AP test, is talking about when they write things in different ways or ask you to use different definitions. Okay, so we're going to recall briefly from last lesson that for any function f of x, f prime of x, known as the derivative of f with respect to x, is given by the limit as h approaches 0 of f of x plus h minus f of x over h. And we got some practice with that yesterday and today, and now we want to think about and make sure we understand why this works. So before you move on to the question here, let's just remind ourselves what we're actually talking about. So we have some function f, and for any value that we choose x, just a generic point, we can find the slope of the curve f at that point by taking the limit as h approaches 0 of the rate of change between x and this point, x plus h. Because notice, because we're taking the limit as h approaches 0, this point here is moving closer and closer and closer to the point x. And what that does is it forces us to hone in on that particular point and figure out exactly what the slope is at that particular point. And what's neat about the way that we've written this is that we haven't specified what the point x is, which means that what we end up with is just a function in terms of x, so that we can plug in any x value that we want and we'll end up with the slope at that particular point. As you might imagine, there's more than one way to go about finding the slope at any one point x. And so your goal is to define the derivative of a function in as many different but equivalent ways as you possibly can. And to help you get started, it would be helpful to consider also that there is some point x minus h out there. And so you might want to think about utilizing the point x minus h to help you find and compute the derivative f prime of x. So go ahead, write this down. It's good practice just to remind yourself and write the definition down again, and also to have a graphical representation. And then spend at least 5 to 7 minutes trying to come up with some different ways of writing the derivative f prime of x. And you're going to want to use a limit still, don't worry. Okay, so hopefully that went well, and I'm sure you were able to come up with at least one. And the most obvious one, at least to me, is let's use this point, x minus h, instead. So in this case, what we want is we want to take the limit again as this h value is getting closer to 0, because that's moving this point here closer to the value that we actually care about. So how would we write that? Well, we're still defining f prime of x. And here we're going to take the limit again, but let's be careful how we're going to define it. So we're going to take the limit again as h approaches 0. And this time, let's make sure we're writing, so take a look here at our definition. F of x plus h is further to the right because it's plus h. If we're using x minus h, this point over here is actually further to the left. So the point that's furthest ahead is actually going to be f of x, and so that's the point we're going to want to write first. Remember, in finding average rate of change, we're using the biggest or furthest to the right value. So we'll have f of x minus f of x minus h divided again. What's the distance between those 2 points? Well, that distance is, again, h. Okay, and the last one that I think is really intuitive is, what if you combine these two ideas? So you didn't just use x and the point x minus h, or x and the point x plus h. You actually just used these two outside points, and guess what? As h approaches 0, these two outside points are still getting close to x. So we can use another definition. You can say the limit, again, h is getting closer to 0. And here the average rate of change that we're computing is between x minus h and x plus h. So x plus h is the one furthest to the right, so f of x plus h minus f of x minus h. Divided by, now let's be careful here, the distance between x minus h and x plus h, well, if you break it up, the distance between x minus h and x is h, as is the distance between x and x plus h. So the distance between these two outside points is going to be, and I'm talking about these two outside points, is going to be 2 h's, or 2h. And this is actually the one that I had us think about at the very beginning of the year in our motivating example that we talked about in lesson 1. So here we've actually seen two totally valid ways of computing the derivative of a function f, and we're actually going to look at a couple more ways in just a second. Alright, so here are the alternate definitions for the derivative of a function. So I'm going to hopefully make this more rigorous in our definition than I did in the previous problem. So the derivative of a function f of x is f prime of x, or the derivative of f with respect to x. And the way that we defined it, and the most common way to define it, is the limit as h approaches 0 of f of x plus h minus f of x over h. And this is clearly illustrated in the graph here. We have a function f. Here's my point x. It can be anywhere, and that's what's great about it. When we take the derivative in this way, we actually just end up with a function in terms of x. So we can plug in any value we want. Here is f of x plus h. Here is f of x, x minus h. And so for this first one, we can just imagine that the limit is making this x plus h point close in on our point x. And so we're taking the average rate of change of these points that are getting closer and closer and closer, and by taking the limit as x approaches 0, we're getting as close as possible and finding the slope right at that point. Now, the second one, you'll notice I've all of a sudden gotten rid of h. What have I done? Well, I haven't done anything crazy. I've just defined it and written it in a different way. And some people like to do this. They like to, instead of using h, they like to use, and I spoke about this at the beginning of the year, they like to use the convention of saying, instead of x minus h, they'll say x minus the change in x, written delta, or this triangle here, which is the Greek letter delta, x, which means change. Delta means change. And also x plus the change in x, or delta x. And so what we've done here is just rewritten the exact same definition, except using delta x instead of h. And that's common as well. I like delta x and h equally fine. They make the same amount of sense to me, as I've obviously done this many times over. But one may be more intuitive to you, and so that can be the one that you use in your mind's eye. All right, and here we have f of x minus f of x minus h over h. This is the one we talked about, right? Here we're thinking about this point, which is h units behind x. And this point is now approaching x, and so we're taking the average rate of change and the limit of that as h approaches 0, which is forcing our slope to be perfectly at that point x. And of course, I could also write this as delta x, and so I would just, instead of the h's, have delta x, and I'm not going to write that because you can get that, and if you want to rewrite it, you can. And then, of course, here is the one that we also talked about, where we're using both of these points, right? Both x minus h and x plus h, and actually coming towards x from both sides. And so here we have to include this extra h because these points are 2h away from each other. And so all four of these are going to accomplish exactly the same thing. They're all going to allow us to compute the slope at any point along our function f. Now there's one other commonly used way, and this one is slightly, I think, less intuitive based on what we've drawn here. And so to help us understand this, I'm just going to imagine we have some other point. Let's just call it A. Okay, give me any point A. All right, and let's say I want to find the slope of my function f right at A. Okay, and so what I'm going to do, let's just think about this. Let's take the point x, and let's calculate the slope between these 2 points, and then let's take the limit of that as x is getting closer and closer to A, which means that we'll be looking at the limit as x approaches A. So this is what we're doing here is we're finding the derivative of f at A, or with respect to the point A that we choose. And the way that we do that is we take the limit as x is approaching A of our function f of x, right, defined at x here, minus f of A, because it's further to the left. And then the distance between these 2 points, well, it's just whatever x is minus whatever A is. That's the distance between the two. Okay, x minus A. Okay, and so what this does is this gives us the derivative at any point where x is equal to A. And so what you'll notice is that when I'm done computing this, I'm going to get some function in terms of A, if you will. And then once we have that function in terms of any point A, we can always put x back in that equation so that we have the derivative of f with respect to x. But this is just an interesting way of thinking about finding the derivative, and the convenient part of that is that our denominator then has a slightly different look, which can be convenient in some situations. Now, from this, there's actually another way that we can define this, and the reason I bring this up is because we notice that, look, this is going to be the derivative with respect to A, and sometimes it's annoying to then have to plug that x back in. So you could think of, well, how could I use this idea but end up with the derivative with respect to x? And what that means is that instead of x approaching A, we actually want our value A to approach x. And really all we're doing is rewriting this with the opposite motion. But what it will give us is a function in terms of x. So you could take f prime of x, that's the derivative with respect to x, and the way we could compute it is we could take the limit as some point A approaches x of f of x minus f of A over x minus A. And here, the only difference is that now we'll end up with a value in terms of x because A is approaching x. So now when we see an A, when we're all done, when we've simplified to the point where we can plug in, what we're going to end up doing is we're going to plug in for all our A values an x. So what we'll be left with is some function in terms of x, whereas here we were going to plug in for x, wherever we saw an x, an A value, which would leave us with something in terms of A. So this version here allows us to end up with something in terms of x. In other words, we won't have to do this anymore, okay? But if you use this definition here, you will, okay? So either one, they mean exactly the same thing, and they allow us to kind of change up the denominator in here. If all of these seem really confusing, I encourage you to spend a couple minutes, come by, ask a couple questions, but always know that you can rely on the first definition of the derivative. It will always get you the correct answer, just as each of these will as well. All right, so here's a problem for you to try. So here we have the function square root of x, and we want to find f prime using the definition from number 5. So go ahead and go back to your definition number 5 and use that to find the derivative f prime of x. All right, so I used the first way, and I want to show you how what we end up with is something that we need to then convert back into in terms of an x value. And so what I'm trying to do is write f prime of x, and so what I do is I take the limit as x approaches a, and you'll notice that what I'm doing is purposefully leaving this in terms of x because what I want is a function in terms of x. However, when I evaluate this limit, I'm going to end up with something in terms of a. And we'll see why. So f of x minus f of a over x minus a. And I'm going to take the limit again. And here I've got the square root of x minus the square root of a over x minus a. Just apply the definition. And now I want to rationalize. Remember, whenever I have some square roots that I'm dealing with, if I multiply by the conjugate, I will end up without those square roots. And that would be really nice. Of course, because I want to cancel out this x minus a, because that's giving me a little bit of trouble. And so when I FOIL this out, I end up with x square root of x times square root of x, which is x. The middle parts will cancel, and then I'll have negative square root of a times positive square root of a, which is just negative a. And so now I can cancel the x minus a in the numerator and denominator, and all I'm left with is what I was multiplying the denominator by, square root of x plus square root of a. Well, I can plug a into that, no problem. So now I'll have 1 over the square root of a plus the square root of a. And that will give me 1 over 2 times the square root of a. But remember, I want f prime of x, so I would need to rewrite this with x instead of a, because I want to evaluate it for x values. Okay? Now, the way that I could have done this so that I don't have to, plug this value back in, is I could just, instead of as x approaches a, I could do this as a is approaching x. So I'll go ahead and do this very quickly so we can see. F prime of x will be equal to the limit, this time, as a approaches x, of f of x minus f of a divided by x minus a. And here, once again, I'm going to have the limit as a approaches x, and just to steal some work that we did above, because I don't want to have to redo it, I'm going to end up with the same thing. I'm going to multiply by the conjugate, and I'm going to end up with this. And let's just go to this point, because at this point I plugged in for all my x values a, and that gave me this. But now I'm going to plug for all my a values x. So I still have 1 over the square root of x plus the square root of a. And now I can substitute in for all my a's an x value, because I won't have 0 over 0. And when I do that, I get 1 over the square root of x plus the square root of x, which is just 1 over 2 times the square root of x. And now I don't have to do any change of variable. It's already in terms of x, which is golden. And so I can say f prime of x is equal to 1 over 2 times the square root of x. And so now I can compute the slope of the square root of x at any x value I want. And I encourage you to try it out. Maybe plug in like 4 or 5 or whatever. Notice what the slope is at that value, and then go take a look at the graph of the square root of x, and you'll notice what the slope is doing. We talked about this a lot in Algebra 2, right? If I graph the square root function, it looks like this. And I must have asked you 1,000 questions about how the slope changes as you move on. And you got very good at recognizing that this is getting shallower and shallower as we move out towards bigger and bigger x values. And so what you'll notice here is that the derivative, which measures the slope, as x gets bigger and bigger, the slope's going to get smaller and smaller and smaller. And it's going to get closer and closer and closer to being perfectly flat, but that's only for really, really big x values. So hopefully this is kind of tying some things together. You're getting used to using some different definitions of the derivative, and also learning how to take the derivative of some different types of functions. All right, the last thing I want to talk about is different ways, different notational ways of writing the derivative. And remember, we watched that little video about how there were 2 inventors of calculus, and since there were 2 different people, the way that they described the derivative, even though they both came up with it, they wrote it in a slightly different way. And that had to do with the way that they kind of proved the derivative. One took more of a geometric method, and the other one thought of it in terms of these infinitesimal differentiations and whatnot. And so because of that, they have different notation, and all of these notations are still used today. And so it's important that you know what someone's talking about when they throw this notation out. So the way that I'm going to kind of help us understand this is that a function can be written as f of x, right, which helps you understand that it's a function of x. X is the independent variable. Or you can write it as y equals, and then you have something in terms of x over here, and so it's just understood when you look at it that it's in terms of x. So similarly, we can write f prime of x, which is the derivative of f with respect to x, and it's the way that we say it is f prime of x. And sometimes you can abbreviate it and just say f prime because it's understood that it's of x. Okay, so similarly, you can say, as you might guess, y prime. And this says y prime. And this, it just means the same thing, right? It's the derivative of y, or, the derivative of whatever our function is. But it's not telling you exactly what the independent variable is, just like this isn't. All right? Another way of writing it, which looks much different, is dy over dx. Okay? And the way this is said, there are a couple ways to say it. You can actually just say dy dx, so dy, and then a pause, dx. Or you can say the derivative of y with respect to x. And here I've written WRT, it's a common abbreviation for with respect to. So you can say dy dx, or the derivative of y with respect to x. And this means exactly what we were talking about just before, the derivative of y, which is the change in y, or the slope of your function, with respect to the variable x. Okay? Another way of writing the derivative is df dx. This is a little less common, and you say it exactly the same way as you would dy dx, but it just puts a little more emphasis on the function. So the way that you would think of saying this is the derivative of f with respect to x. And there it just emphasizes the function's name, right? So here this is emphasizing that it's the change in y, and names both of the variables that are being used, right? Y and x, right? The rise over the run basically is what it's saying here. And this is emphasizing that you're taking the derivative of a function with respect to x. Again, these all mean the same thing. They're just different ways of writing it. And then the last way, and kind of the most complicated and weird way, is d of f. This is a little bit much. But the way that we would say this is d dx of f at x. Yes, I understand. And I'm not even going to bother writing that, because what you want to think of when you see this is the derivative of f at x. Okay? There you have it, and this just really emphasizes that what you're doing when you take the derivative is making an operation on f. And so while this is the most annoying way of actually writing it, it might make the most sense in some way, because when you take the derivative of f, right, remember you're going through and you're taking the limit of basically the average rate of change, or the secant line. And so this kind of emphasizes the fact that you're making an operation, taking the derivative with respect to x of f. Okay, so we'll see these often. The prime notation here, these little things, these are the convention of Sir Isaac Newton. So he used prime notation, whereas Leibniz used this notation. So this was Leibniz. And I did spell that right, I have to check. And over here, the prime notation, this would be Newton. So if you have a particularly favorite scientist, that's the one you can use. Right, here are a few problems for you to try. You should be able to easily find the derivative for all of these, but I want you to get used to the different types of notation, and you can experiment with different definitions of the derivative. So if when we were discussing there was one particular definition that made the most sense to you, go ahead and use that one. The most common ones that are used are the one that we started with, obviously. The limit as h approaches 0 of f of x plus h minus f of x over h. But also the last one, number 5, if you go back and take a look, is also really commonly used and can be even more efficient in some situations. So it's totally up to you. It's your call. Make sure you have a completed solution for each, and I think you'll find number 5 to be pretty interesting and neat.